Okay, let's get started with this one. Welcome back to Violent Earth.
Previously on X-Men.
Great show. Great show. Doesn't hurt to start off with a little bit of silly stuff here, right? So during the last couple of videos, my son was the only one in the room, and he was over there telling me I'm a chatty monkey, right? As you all probably realize, I do chat a little bit, right? So that's why some of these videos have gone on a little bit longer, as lectures sometimes do, even in class. Now, as I'm looking at the video material and as I've uploaded some of this stuff, it is substandard. It's subpar. The screen is quite a bit is washed out. The noise here in the lab, or at least the echoing of the lab, it's not perfect, right? These are the first stabs at trying to get this series of videos or this course up on some sort of digital media material that folks can look at. So, it'll be a work in progress, and maybe over the next couple of lectures, I'll be able to change my format. But that video, as I was doing, last week on Violent Earth, it made me think of Cyclops' voice in that intro to the animated X-Men series, previously on X-Men. So, so really, that was what we covered last time: chemistry, layers, rocks. But today in Violent Earth, what we are looking forward to is a little bit of actual violence in this class, right? Some grandiose natural violence that is unprecedented in anything since this time, right? This is by far one of the most violent things that has happened to our planet since the birth of the solar system, or at least the birth of our planet. And this is what we're going to focus on today, or at least get to by the end, is the giant impact hypothesis. And I say this is unprecedented by anything that's happened since, because this was almost a complete Earth disruption. This was a huge impacting event where the planet itself was obliterated. And by Earth, or by planet, I don't mean just Earth, I mean this planet was obliterated and basically ceases to exist in part of this hypothesis. So I do want to point out that word. This is a hypothesis. This is an example where this idea, this hypothesis, it's been tested. We have a body of data surrounding this, but it is not enough that we have a nail in the coffin. It's not an overwhelming amount that there's no other possibilities. This is just basically the best thing we have going now to understand the origins of the moon, the origins of that big, bright orb that's out there in the night sky about once a month. We get a full moon. All right, but to first of all, we better step back a little bit and talk a little bit about the origins of the solar system. It's always good in a physical science class relating to the Earth systems to talk more about the heliosphere itself. Now, we're not going to dwell on it. We're not going to spend a whole lot of time talking about it, but today this is the one chance in Violent Earth to talk a little bit about astronomy and cosmology and the rest of the heliosphere outside of the other Earth systems. So what we're looking forward to covering today, the universe, a little bit of our solar system, getting closer and closer to our Earth system. And this is an image that will show up later. I better move the mouse because the mouse cursor here is as large as the planet. But over here is a to-scale image of the Earth, the blue marble, and way far away, barely visible, this little tiny speck, the moon. And that's actually to scale. It's a common pet peeve of a lot of scientists to look at images online, or at least sometimes in a textbook or to our conception. People are shown images where the solar system can fit in one picture, right? You can see big old Jupiter right there, and then Venus, over here, and they're kind of comparable in size, and they're not all that far away. But really, these things are immensely far away, and I really like this to scale diagram showing that. Hey, origins of the universe is probably where we should start all of this. Origins of the universe. So back in the day, comic book artist Stan Lee, wrong universe, though this is a really great universe, and I'm really excited for the in-game Avengers that will be coming out here in a couple of months. But let's leave this behind. I'm no expert in Marvel or this universe, but a little bit more of an expert in the Earth system sciences. So I better stick with these details and let the other comic book YouTubers cover this universe. Okay, let's start. It's always convenient to start here. This is the Big Bang Theory, kind of in one diagram, not to be confused with the popular television show. A little pop culture reference there for you. It's a funny show, and I like this show. They make fun of geologists. Sheldon's always ragging on us. We're the dirt people and stuff, but really what he doesn't understand very well with his small physics brain is that this is where we live, right? It is the Earth systems that is really the grander perspective than the physics. Though, there is no one science that's better than the others. This is all a team. This is all a team of us that work together to understand the greater world around us. So, though he can rag on geologists, and maybe I'll, rag a little bit back, we're all in this together. Back to the Big Bang Theory. This is another really good example of something that is not a hypothesis. As mentioned with the main topic today, which is the giant impact hypothesis. The Big Bang, however, did start as a hypothesis, but the overwhelming amount of collected data always seemed to support this hypothesis. And that is how this has been elevated from a hypothesis to now a theory. There's really no really good rivaling data sets. There are really good rivaling hypotheses that are out there, but the data sets from the larger perspective of the cosmos don't support the others quite as well. They don't match quite as well as they do with the Big Bang idea, the Big Bang hypothesis. So the Big Bang, just really simply with my small geologist mind, Sheldon, to the best that I can really understand this, the singularity, and that's shown right here. The singularity, all matter began as a single infinitesimally dense and small point, and when and it exploded, right? It went bang, for lack of a better terminology. It went bang, and the cosmos exploded from that point. Now there was, it's very difficult to discuss anything before the Big Bang. There may have been nothing before the Big Bang. Time didn't exist before the Big Bang. Space didn't exist before the Big Bang. So it's kind of a mind-bending thing to think about stuff before the Big Bang. Or how did that occur? Or what is the bang, the singularity material that exploded out? What is it exploding out into? What is it expanding into? These are really big cosmologic questions, and I have no answers there, right? We can dwell on a few YouTube videos that are out there, or read a few of these textbooks, or maybe go get a bachelor's level degree or graduate level degrees in this, but we don't have these answers. There are a lot of people working on these answers to get closer to them and some of these details, but it is not a known thing, right? There are a lot of ideas and hypotheses in many data sets, but we don't know a lot about, well, anything about before, and then there's a sort of a large area that we don't know a lot about, period. What we do know and is detectable is the cosmic microwave background radiation. That is the most distant detectable light, which is light in the form of a microwave that we can detect. And that information, which is kind of shown right here, but it's shown as kind of a tilted view, so it's not the best view of that. Google that, of course, if you'd like a better image. This cosmic microwave background radiation does show asymmetries. So this shows that it's not expanding at an even rate everywhere, right? That it's not all just going all out and emanating in one direction at the same rate everywhere, at least to my knowledge. And it's from things like this, looking at the very furthest back that we can tell, that's the origin of the multiverse hypothesis, right? That there are maybe not just our one verse that we live in and occupy, but maybe there are multiple universes that exist outside of our own. And this is very different than the popular sci-fi idea of parallel universes, which again we might get to see in the whole Marvel thing, or some of these other types of overlapping multiple reality universes that exist in sci-fi. But that's not what we're talking about here in the scientific hypothesis of the multiverse, that there may be another universe or multiple other universes, or the multiverse, that exists outside of this. Now, beyond the cosmic microwave background radiation, what we can easily detect, and you can do this with a telescope, actually you can do this with your own eye by looking out at the cosmos, we detect all of this ancient light with our eyes. Now, when you and I are looking out in the cosmos with our naked eye, or even with a standard telescope, backyard telescope, or an expensive backyard telescope, most of the things that we're looking at exist within our galaxy, within the Milky Way galaxy. All the stars that you see, all 6,000 or 9,000 stars that you can see out there in the night sky are within the Milky Way galaxy. But there exists outside of that a lot of other material. Now, we'll come back to that in just a second. But all of that material is what was expelled from the singularity in the Big Bang. And all of that material, from everything folks can tell right now, and this was a really big observation to support the Big Bang hypothesis, is that material is rapidly is expanding away. Everything is expanding away from one another. So you can think about it as I've seen the analogy of baking cinnamon bread, right? If you have a dough with little, what do you call them, raisins that are embedded in there. And as the bread loaf baked, it expands, and each of the raisins get a little bit further away from each of their neighbors. Maybe some of them get a little bit less further away than other of them. So we can detect that with with individual galaxies expanding at different rates. But in a larger general sense, the universe is expanding. And it's not just expanding from this point and went boom, and then is slowing as it's expanding. No, actually it's accelerating in its expansion. And I find this just mind-blowing. You would maybe think, when any normal explosion happens, when you put, say, a aerosol can in a fire and it explodes, as it emanates out, it slows. It slows down until eventually all the material falls back down to the earth. But not the same for the cosmos. That analogy of an explosion doesn't actually work to talk about the Big Bang, because this explosion is continuing to expand. So if that analogy is true, we're at the very beginning of that explosion, which is very, very interesting. And that explosion, or this Big Bang that occurred 13.8 billion years ago. Remember giga, like a gigabyte, billions of bytes, giga-anon, 13.8 billion years ago, right? So that's 13,800,000,000 years in the past. And the system that we're going to focus on in this course, of course, the Earth system, or the solar system, centered by the sun, the big bright star out there that we can see during the day, takes up a very small fraction of that, right? Close to 30%. it's only about 4.5 billion of those years long. So the rest of the course is going to focus on the catastrophes of the last 4.5 billion. But today, in this first 10 minutes, we're going to breeze through the whole 13 billion years preceding that, or 9 billion years preceding that. Okay, so the universe is expanding and it is accelerating in its expansion. I have linked here a YouTube video, a little bit, they can explain this much better than I can. This is from Science Rant, I think. How large is the universe? I should also link this in the comments below. Easily YouTubeable, but this is a really good, about half an hour long video that does a really great job at explaining not just the hypothesis, but also how we know these things, right? How we've detected any of the limits of the universe and whatnot. Now, the image that's behind this link is what we call the observable universe. So though there's a universe that's out there, there's a whole lot of stuff, we are limited by our capabilities of our sensors, our eyes. We can only detect light, or the whole electromagnetic spectrum from X-rays to microwaves. We can only detect those things if they're not blocked by other things, right? So what's shown here in the dark colors in black is all the stuff that we can't actually observe. Light from those places can't actually make it to us. So there's the universe, there's the known universe, or kind of the limits of that, which evidence from the cosmic microwave background radiation, and then there's also the observable universe, the stuff that we can actually look at with with different devices. And this image also shows some of the things that we haven't observed yet, but we have the capabilities to observe at some point, or with some instruments, whether that's short in the future, or whether that's when such and such new telescope is built. We still have more that we can observe, and we know that, and I think that's pretty cool, as we know that there are limits to our observation, and we know that we have not reached those limits, so it isn't all known, right? I think there's something very elegant in that. Then I have another link here as well. This is what's called the scale of the universe, and instead of trying to show the universe in whole or anything, this is an interactive website, and again, I'll link this in the comments below on maybe this video, but this is a portion of an assignment for the Violent Earth students. So this link will be accessible to you through the Canvas site. But this site is really neat because it starts out, it's all in log base 10, and it starts out at the human scale, which you and I live at about the 1 meter scale, and we tend to think about things at that scale, right? Ants are smaller and elephants are bigger, right? And those are two things that live at a slightly different scale than we do, right? They live at the centimeter scale or at maybe the decimeter type of scale. Now, even that's a little bit big for an elephant probably to think, if they think about those sort of things. Now, the point here is there is entire worlds that are small, well, worlds not literally, but worlds in this very figuratively, worlds that are smaller than us. Think of the ant, but even smaller than the ant, the water molecule, the atomic particles, as we talked about with chemistry the other day, and smaller than that, the subatomic particles, and smaller than the subatomic particles, all the way down to an idea called the string theory, right? Excuse me if it's a string hypothesis or string theory. I might be, messed up by popular articles that show up, but the string idea is a fabric that holds everything together, right? And that is at a much mind-bendingly smaller level than the subatomic particles, right? There's a huge gap between what made the quantum foam, or what the Planck lengths that may make up the string world and the string hypothesis, and then things of the subatomic particles. Now, equally, there are huge gaps above us, and interestingly, we are closer in size to the biggest things than we know of than to the smallest things we know of. I think that's interesting, and that's really shown here very well on this website, where you can move the scale bar to the small stuff, but also to the big stuff, which would, of course, include, it's easier for us to think about this, which would, of course, include elephants, or, say, redwood trees, or the entire planet Earth, or our neighboring planets, those that are smaller than us, like Mars, or comparable to us, like Venus, or larger than us, like Jupiter, the big brother of the solar system that's out there, a big protective brother, but also the solar system itself and the star, right? And then there are things that are much larger than that, like the nebula that we'll talk about here in a second, and galaxies and superclusters, and on to the entire universe itself. Now, I encourage anybody interested in this scale to go to visit this material. Now, there's also in the supplementary materials for those students who are registered in the course through Canvas, in the supplementary materials, there's a lab exercise that I often do with the rest of my Earth System Science students on scale, on trying to understand why we scale things. And that goes back to that, the fifth big idea, to really try to understand things. We have to scale them down to the meter level, right? We've talked about this before. So please visit that lab. Also, if you're interested, again, from my colleague back in Wisconsin, Jeff Pinota, thank you very much. I still have that lab and still use it. It's a great lab. Okay, now let's focus in a little bit more towards our neighborhood. We're still very far away from being able to focus on the Earth, but this is a computer image that is the best way that we can conceptualize our local supercluster of galaxies. So our galaxy, the Milky Way galaxy, or our closest neighbor, Andromeda, would be represented by one end of one of these lines. And then each of these lines together are representing our supercluster of all of these galaxies that are relatively grouped together comparatively to, this is the Laniakea supercluster that we are a part of, comparatively to the Perseus Pisces supercluster that would be our closest supercluster near us. Now, the reason for bringing this up is just to show the multiple scales of things, right, of collections of things. The other day, we focused on the collection of atoms together that make up molecules that then can bond together, once again, to form things like minerals. And those are collections of matter. This is another collection of matter, essentially. There's another good, great video of this, the Laniakea, our home supercluster. Now, I'm not going to play the video while I'm doing a video at this instant, even though I did it with the cool X-Men video. But again, this is something that is easily searchable on YouTube or Google. It's a really interesting material, and again, just serves that purpose in this class, that it is interesting to think about these different levels of matter. Now, on that last page, there's, of course, the ideas or what are called fractals, right? Not necessarily an idea, but the phenomena of fractals. That the same patterns are, in many times, observed at multiple levels, all the way from way down there at the subatomic level to the much larger universe level. And these aren't exactly fractals, but these are patterns that I like in my life, that are exhibiting the same behavior, that are repeatable patterns, if you will, at many different levels here. So here's the neural network, the brain network of neurons that we have that are firing in my mind or in your mind right now, that are not just because we're thinking, but that are allowing all the sensory input to come in, whether it's light or whether it's sound or whether it's brain rattling data. The neural network and the paths between neurons and the dendrites, the dendritic system, is very, very similar, strikingly similar to the pattern of, as we just looked at with Laniakea. Now, that was an image that is meant to show some data, but if we, so that was generated by humans and looks that way because of the mathematics and data. That's not reality. But if we step back and look at the reality of how superclusters are arranged out there in the cosmos, at least the best conception of that we have is that they have a cosmic web. And so this is from a Scientific American article, I want to say back in 2011. Excuse me for not having the reference listed here, but it's a fairly popular image and popular article. And again, a quick Google search, something like Cosmic Web, can easily show the original source of this material. Now, I think this is fascinating, right? And I'm not the only one fascinated by this, and that finds this same relationship elsewhere in nature. The great mycologist Paul Stamets, the great Paul Stamets, is a great mycologist, and another really great YouTube video that is linked here is 6 ways, I believe it is 6 ways mushrooms can save the world. I know that's a really, really big kind of thing to say, mushrooms can serve the world, but Paul has some really great definitions on this in a really great book, Mycelium Running, that supports a lot of his dealings in mycology and understanding the mycelial network, or the underground world, what does he call it? Not the World Wide Web, but the World Wood Web, I think he calls it. That is the mycelial network, or fungal hyphae. So the living mushroom mostly is an underground hyphal network that looks very much like this, and then the fruiting bodies of mushrooms come up periodically in the spring or in the fall when the rains come. Now, he noticed years ago and had proposed that the mycelial networks were the original, nature's original internet. And I think that's fascinating. That's why he calls it the WWW, the World Wood Web, I think. And so he has also argued that this pattern is observable in the cosmos, in neurons, and if you were to make maps, like as computer scientists do, of the internet nodes, it looks very similar as well. So really fascinating stuff here, again, at the scales that we live at and can observe. Okay, now coming in slightly, a little bit here, a slight tangent here once again, the universe, our universe, the one that we can observe and see, really probably the only universe that we know of, 300 billion galaxies, each containing 100 to 300 billion stars. That's a big number, right? If you multiply 300 billion by, say, 200 billion, somewhere in between, you get a big number. And Carl Sagan long ago had stated, or at least had made this, or had come to this conclusion that more stars in the universe than grains of sand on Earth. And now I think that's a fascinating statement, and I'm not the only one to think that that's fascinating and think like, I wonder if that holds up by the math. Fraser Cain, who I believe publishes the magazine Universe Today, excuse me again if I have that incorrect. I know him from a wonderful podcast with Pamela Gay, the astronomy podcast. Really wonderful information about everything, not necessarily in the cosmos, but by observable astronomy. So the solar system, planets, being able to look at the night sky, and a lot of other universe-like material. But he took on this question in this video: are there more stars or grains of sand? And I'll let you watch that video to find your own conclusions. But let me tell you, how often is Carl Sagan wrong, right? So that gives you a little bit of an idea of what to expect in that video. All right, now really focusing in a lot more closely, here is our closest neighbor. Our closest neighboring galaxy in the Laniakea supercluster, or the Virgo cluster of galaxies. This is the Andromeda Galaxy, and it may look familiar to you because if you have ever seen an image of the Milky Way galaxy, they're showing you this. We live in the Milky Way galaxy. We can't see it. We've never been outside of the Milky Way galaxy. We can't go outside and turn around and look back and take a picture of it, right? Not happening. But from what we know, or the observations suggest that our galaxy, the Milky Way galaxy, is the same type of galaxy. So there's several types of galaxies that are out there, all of different shapes and sizes and radial patterns. And the Milky Way galaxy is supposed to look very similar to the Andromeda Galaxy. So it's kind of the Andromeda Galaxy is kind of a poster child then for understanding what our galaxy looks like. Andromeda also, I think this is also extremely fascinating. It's the only piece of light outside of our solar or outside of our galaxy that you can see with your naked eye. Now, there's other things that you can see with a telescope, other galaxies, but if you know exactly where to look within the Andromeda constellation, that's near Cassiopeia, the big W over there, kind of to the side of the Big Dipper, which is really easy to find. You can find the W, you can find Andromeda, and from Andromeda, you can find, if you know where to look, if you get really good at practicing and finding this, you can find this fuzzy, kind of hazy football, and you can see it barely with your naked eye. It's so cool and fascinating to see on a summer night out camping or something like this. I've shown many people this out camping while we're out having fun doing geology. Now, also, really fascinating, besides just being able to see this piece of light that's outside of our galaxy, the light, because light is moving fast, but not infinitely fast, right? It's only moving at light speed, for gosh sakes. But it takes a while to move through the cosmos, even at light speed. So at light speed, which is how we measure distances in, of course, interstellar space, is there are a few other types of ways to measure this or to say this, but the distance that light travels in a year is a measurement of space. So even though it's called a light year, that's not a time, that's a measurement of space. The light that leaves Andromeda is 2.5 million years old. 2.5 million year old light. So that means it's 2.5 million light years from us. So when you do go out and look at the Andromeda galaxy with your naked eye, that light has been traveling since the Ice Age of Earth, since deep in the beginning of the Pleistocene, the Ice Ages of Earth, before it has come to you. So when that light left, there were no Homo sapiens, right? There were barely Australopithecines when that light left that galaxy. I just think this stuff is really, really cool, and hopefully you do too, and are at least inspired by how cool I think it is, man. Okay, now focusing in quite a bit more, we now find ourselves on Earth. And this is what we see of the Milky Way galaxy. This is a wonderful photograph that was taken in 2012, 2013, but was the Guiding Light to the Stars by Mark Gee. He was a winner of the Astronomy Photographer of the Year photo. And this is great. And this is showing the arc of the Milky Way galaxy as we see it. So the Milky Way galaxy being a disk, and we're at one spot within this disk. Actually, this should be more like a frisbee, like a disc out here. And we're at one spot of this. So sometimes, in the beginning of the night, say, you're looking out into the night sky and you can see this side of the galaxy. But as the Earth spins, we see a different part of the Milky Way galaxy throughout the rest of the night. So sometimes of the year, when you're out stargazing, you can see the Sagittarius constellation, and that is very near the center of the galaxy itself. So we're looking towards the galactic center. Now, in the winter months, like right about now, when you can see Orion, we are looking towards, we're looking away from the cosmic center in those evening stargazing experiences. So I think this stuff is fascinating. I really like stargazing, and upcoming this term is also the astronomy general science class here at TVCC. So here's what we can see of the Milky Way galaxy, not that disk shape that we can see of Andromeda. All right, we're finally closing in on Earth here. Okay, so within the galaxy itself, the galaxy, as we know it, is composed of a bunch of particles of material, right? I think sometimes it's best to describe this as dust or cosmic dust. I hear it referred to sometimes. When I think dust, I of course think silts, right? I think silts are clays. I think about Earth's materials, and I don't conceptualize this kind of dust stuff very well. But I think it's a collection of gases that are loosely bound together as particles. So this is hydrogen and helium, maybe some lithium and beryllium. Some of these lighter particles of the periodic table that are abundant out there in the cosmos. This is not silicate-based dust, which makes up most of the Earth, though a very fine, small amount of this stuff out in the cosmos may be. Now, the galaxy is mostly composed of this dust, which has mass to it. Now when we're talking about dust in those particles of gases, we're talking about stuff. It actually is matter. These are those atoms that were shown the other day, the generic atom. That's matter, right? The protons and the neutrons, they weigh something, right? They have some sort of weight to them. And that weight, or one mass, when it is coming near another mass of similar or larger size, doesn't really matter. Those two masses, they exert a force on one another. We call that force gravity. We'll get into this in just a second a little bit more explicitly. But the galaxy being made of this dusty material and these particles exerting gravity or the gravitational force on one another, there accumulates these large areas of dust, these dusty, dirty places that we call nebulae. And this is the Corona Nebula, just a beautiful, beautiful place. I think these cosmic images are just extraordinary and beautiful. And these nebulae then are the birthplace of stars. This is where all of that mass, those dusty particles, whatever that dust kind of stuff is, those dusty particles, they're exerting so much gravitational force on one another that they're all affecting one another, and they end up with some sort of angular momentum. And their gravitation, the gravitational force that they exert on one another, contract them together to eventually form such a large accumulation of this stuff that they form a star, what we refer to as a star. So here's the Carina Nebula, excuse me. In that process that was just sort of discussed there, that's called stellar nuclear synthesis. So stellar for stars, synthesis for making, and nucleo for those nuclei, the atomic, subatomic particles that are the nucleus of an atom that are creating and manufacturing together heavier and heavier particles. So stellar nucleosynthesis is the sort of process of the origination of stars. Now this is another nebula. This is the Pillars of Creation, oftentimes it's called, another birthplace of stars, another nebula. Just extraordinary and beautiful images, very popular images as well. So a couple of words to add to these slides. Gravity is pulling inward, creating an accretionary disk. We'll take a look at that in just a second. Dust is accumulating. The heavier stuff is why I have this in quotation marks. Dust, whatever that really means, I don't have a great conceptual understanding of that, accumulates in the interior, the heavier stuff, the stuff that has more mass, while more of the diffuse gases accumulate on the outer portions of these accretionary disks. Okay, disks is really important here, like a frisbee. Just keep thinking frisbee. Then the dense ball in the center, as those particles are exerting the gravitational force on one another and accumulating together, that becomes an ever-increasing ball of gas. And then that dense ball of gas together, all exerting forces on one another, eventually ignites. Not like igniting with fire, but fire is a pretty good example of bonds that are breaking. And that's really what's happening here. The fusion reactions, instead of bonds breaking and emitting photons, instead what's happening here, two particles, individual particles, hydrogen, two hydrogens, two different isotopes of hydrogen are fusing together, fusion. Hydrogen 2 and hydrogen 3 isotopes are what are shown here. And as they fuse together to create helium, manufacturing a brand new element, an element that doesn't exist in this system beforehand, maybe at small amounts, new element is created by the fusion of these two. Again, remember the periodic table discussion the other day? If you were adding protons together, then that is what we refer to as a new element, a new material. But that leaves out a neutron. So what's expelled here is a neutron, or a whole bunch of energy, that isn't used in that reaction. It's that neutron, after the ignition of these stars, it's that neutron that becomes the photons, or that are the photons that are expelled from the sun that come across as solar wind to bombard our atmosphere, our geosphere, or even us, our biosphere, with a lot of energy, so it feels warm to us. But that energy is also absorbed by plants in the photosynthesis process. Okay? Other things we're going to talk about later in the class, but it's really exciting. So now we've gone from Laniakea and the supercluster and down to our sort of local neighboring systems, the Andromeda and the Milky Way galaxy. Now we're in our solar system, and now we have an ignited star in the interior. We have a sun. That's where we're at right now. And I think it's important to say here, a conceptual way to think about this, I like this anyway, hydrogen energy, when we think about one form of hydrogen energy in the form of fusion, that is what is going on here in our sun, right? About 150 million kilometers away from us. So when we're absorbing photons with solar panels, right, on outside, and creating what we refer to as solar energy, that actually originated as a different form, a nuclear energy that's being manufactured in the center of the sun, or hydrogen fusion. Okay, this is great stuff. We can also think about this as star heat, and that's probably how I'll refer to it for the rest of the course. Now, let's discuss that accretionary disk a little bit more specifically. The accretionary disk here, here's a really good image. Again, another thing from Universe Today that really, I think, is a good conceptual idea, the accretionary disk, where we don't have a whole lot of stuff around the center where that sun ignited and that material is blown back away from that. So basically, any closer than Mercury, there's no material that exists there. And then on this rest of the accretionary disk, this diffuse material in orbital motion around that massive central star, that massive central body. This diffuse material has some angular momentum as it's going around, orbiting or revolving around this central body. But all these particles have different sizes and different masses, and they begin accumulating together. They begin smashing into one another, probably by this effect of gravity. And even probably by accident as well. Maybe they're not gravitationally pulled to each other all the time, but one thing has a crazy trajectory and it hits another thing, right? All of these processes, these random turbulent processes are possible, but what is really happening here is the mass is accumulating together. However that's happening, multiple ways, that accumulation of material is resulting in bigger and bigger masses of material that we can begin to call planetesimals. Now, these planetesimals that accumulate by the collision of particles, they're small. And there are probably hundreds of these things in the origin of our solar system. And it is multiple planetesimals together that collide to create larger protoplanets and planets. Now, we'll get there in just a second. But these planetesimals, these are odd, sporadic little things. The reason that they are sporadic is, again, going back to the gravity equation. This mass is rapidly accumulating more mass. Well, if that mass is getting larger, it's exerting a larger and larger gravitational force on all the rest of the stuff. So not only is it a kind of a positive feedback that it's accumulating more material as it gets larger and larger, but also the distance between the sun and this body is dependent on the mass of this particle, right? Now, as this gathers more and more mass, the gravitational force between these two objects is greater and greater and greater and greater. So this would begin to drift as it's orbiting closer and closer and closer, like a spiral. It's spiraling inward until it would eventually get sucked up by the sun, and that planetesimal dies. Now, one really interesting thing about our solar system, this is what's called the NEISS or NICE solar formation of the solar system, is as this spiraling inward was occurring, Jupiter, the big brother planet that's outboard of us, the first gas giant, the biggest thing besides the sun out there in our solar system, gathered such immense mass that it began exerting a gravitational force on all of the inner rocky planets, which stopped that drift by balancing out the gravity between those two. And rather than the Earth or all of the other planetesimals that exist in here that eventually become our rocky planets spiraling inward and collapsing into the sun, Big Brother Jupiter helped us out of it, right? And in this sort of anthropomorphic way. So really, our rocky planets, or at least the planetesimals that make up the rocky planets, exist only because the formation of Jupiter occurred first. And the mass was able to save the rest of the planets from being sucked into the sun. I think that's fascinating. It has some really interesting Greek pantheon implications that are there, right? Zeus, the large star of Jupiter by the Romans, has also been seen as a protector of people, protector of humans for the past. And I'm not suggesting that there's any sort of great insight that maybe the people had, but I think that it is a really cool overlapping story of what people had once said 2,000 years ago and now what we know. So let's take a more specific look at the gravity relationship, and I'm just going to breeze over this, but it is really important. Again, supporting details in this class, besides just me sprawling out this material. The supporting details are crucial here. The details are not that important for the big picture, but the big picture is made up of each of these little brushstrokes of details. So the gravity relationship, it can be further expanded on in this YouTube video here. I should have added the name to this, but this is really a video that is explaining this relationship. It's a gentleman that's going through diagrams, and he kind of makes it fun. He's a good science communicator, and I would recommend if you want to take an additional interest in looking more at the gravity equation, then you check out this YouTube video as well. I'll put that in the links below. We'll come to this link in a second. But the gravity relationship here, big G, which is not the same as the gravity that Earth exerts on the rest of the material here, 9.78 grams per meters squared. It is a different grams per meters cubed. Sorry. Is a force that's specific, or that's the acceleration due to gravity specific to Earth. Now, I'm not talking about specifically to Earth. I'm just talking about gravity in general, right? So this is used to explain any gravitational relationship between any particles. You have those two masses, right? Maybe one is larger and one is smaller. That's M1 and M2. And this could be the size of Jupiter and the size of Earth, or this could be the size of me and the size of Earth, right? Two very different scales, but either way, we can understand the gravity between those two things by this equation, plugging in my mass, plugging in Earth's mass, and then dividing that by the respective distance between them. Now, in the case of Earth, I'm standing on Earth, but we're talking about the center of its gravity, so the center of the Earth itself, about 6,000 some odd kilometers, right? Now, that distance squared. So this is an inverse relationship with the distance that they are apart from one another. So this force reduces with the square of the distance. So the further these things get apart, the less gravitational force they exert on one another. And it's a compounding thing, because a little ways away, they exert double less the force, right? So this relationship is fundamental to the creation of the solar system itself. And that's actually what I want you to find here at this next link. You can Google my solar system or follow this link that will be in the comments. And you get to this really great put on by the University of Colorado, this really great simulation to create your own solar system by plugging in different numbers into these units. So here is actually your assignment for today, if you're registered for the course here on Canvas, is I want you to go visit this and to play around with these numbers, to tweak these numbers a little bit. You can add a couple of separate bodies. So here's mass 1, the bigger one. Here's mass 2. And you can add mass 3 or mass 4. But what's interesting here is you can change the respective masses and see how that affects the gravity between them, the gravitational force. You can change the respective velocity that each of these things have, so you can give this a small velocity or angular velocity to this planet and see what happens if this is moving relatively slow or if this is moving fast. Then you can also change the position. You can move it over here. You can move it wherever you want to. Closer to have a larger gravitational force, or further away to have a smaller gravitational force. And this is a really great way. This is really fun, actually, to kind of tweak these numbers a little bit. I say it's fun because my relationship or my conception of fun would be like what do kids want to play with or do, right? And so a few years ago when I first found this, my kids, I think, were maybe 3 and 5-ish, my 2 older kids, and they just sat around, they looked at this thing, they played it, they tweaked the numbers, and they were doing all sorts of stuff, and they played it for hours, right? They see it as a game. So even the other day when I was making this lecture, and I put it up here, my son Ocean was like, hey, I remember that game. So it is kind of like an interesting game that you're learning this relationship of gravity. Now, what I want you to do if you're registered for this course is to create a solar system. As simple as that, right? It sounds as simple as that. But what you will find, hopefully, is that the unique balance here between the masses and the relationship of distance and their relative velocities to one another, it's delicate. It's very special that you have any planets that are circling the star, or orbiting the star, that weren't gobbled up by the star itself, that didn't fly off somewhere and go away from the star, or that didn't accumulate in 1 or 2 larger planets. So that suggests, as people have suggested or known for a long time, that maybe not every star has planets. And that's absolutely true. There are a lot of stars that have planets. So those exoplanets is what we call them. Those are planets that circle other stars beyond our own. There are some 1900 or 2000-ish, last time I looked up on this, known planets that circle other stars. But not every star has a planet around it. And this is probably why, because this is a delicately balanced system that even yields planets in a solar system in the first place, okay? So your assignment is to create a solar system and to record these numbers and then to upload just a simple document with some of these numbers and a statement on what you learned by this balance of these bodies to one another, okay? Moving on back to protoplanets. So we last left off with planetesimals, these smaller, more randomly moving, I mean, they're still orbiting, but they're randomly moving because as they're accumulating mass, they're getting closer and closer to the sun. They're also greatly affected by any larger masses that are in their path, right? If you have 2 planetesimals of relatively similar size that are relatively, in the same orbit around that star, they're exerting a great gravitational force on one another. So their orbits are going to be kind of wonky, kind of weird. That's something you can set up in the simulations to make 2 planetesimals of the same size, really near the same orbit, and you'll see how they affect one another. And sometimes they'll get close to one another and they'll want to wing off out into nowhere, out into space, because of that relationship. Now, to fast forward a little bit more, we don't know what happened to all of the planetesimals in our solar system. Many of those, suppose, would become parts of the rocky planets or the cores of some of the gaseous or ice giant planets are out there in the Kuiper Belt. Many of them probably are still contained within the solar system. And those individual planetesimals, as they accumulate together to make larger planetesimals, eventually they become so large that they're the largest thing at that distance away from the sun, or that astronomical distance away from the sun. So they are the biggest and baddest thing at that distance away, and they're just accumulating the rest of the small rocks. They have then a consistent orbit, an orbit that is not affected by gaining more mass and having a wonky spiral orbit towards the sun, but they are also not gaining they are not affected by any of the masses surrounding them. So you can think of this as Earth not being affected much by Mars's size. So we call those then protoplanets. And this has been the beginning of what we can think of as Earth. Now, interestingly, I think this is really cool too. I love these cool little tangents, as you've noticed. Interestingly, our planet has been doing this anti-accretion thing for the last, 60, 70 years of space exploration. I think that this is pretty darn cool. Over the last 60 years of space exploration, the Earth has actually anti-accreted, so rather than accreting material, we're sending stuff out of this rock, 5,500 tons of that stuff over the last 60 years. So that would be all the space material that we've ejected out. And here's a really good image of a stratus layer of clouds with one of these rockets that is extending above that stratus layer. I think this is a great image. This is something I pulled off of Reddit a while ago. Excuse me, don't have the source for this material either. But this almost inevitably came from the International Space Station. A picture that high up that is looking at one of these rockets coming above the troposphere. Then another image here, the NASA Orbital Debris Program Office. This is what's showing all of the debris that's within near-Earth orbit, right, or within Earth's orbit, all the satellites, space station, all these things that are still within our orbit that we use for communication, for GPS, for satellite television to bring you WWF or WWE or whatever it is. But my point here is I think this is kind of funny, right, is that over the last 4.5 billion years, everything has been accumulating, right? There is small particles that we lose every year, helium and gases, but we've been losing significant amounts of mass in this process, and I think that's pretty cool. Now, to take a look at our neighbors and what we do know of our surrounding neighborhood, this is probably the last time we're going to focus much on the rest of interplanetary space, so the space of our planets. We're never going to return to interstellar space for the Violent Earth class. First of all, this is shown on a logarithmic scale, so every one of these numbers is 10 times further away. So 1 Earth distance, if you take that times 10, right, is about when you would get out here to Saturn. So Saturn is 39 astronomical units away, or 29 astronomical units away from the Earth, which is an astronomical unit is 150 million kilometers away. That's the distance from the sun to the Earth. Now, my point here is first to show you that this has a scale, so it's not to scale, but the scale here is a little bit misleading if you're not used to seeing things at a logarithmic scale. So what these numbers mean is that you expand this out a very, very long ways, right? So this should be 10 of these distances away. This is 100 of these distances away, and so on and so forth. Now, what's really, the reason this is all smashed together is this is an image that was produced in, I want to say 2013, when the Voyager 1 had finally made it to interstellar space. That's the space between stars then, between our star and the next closest star, Alpha Centauri out here. There were signals as Voyager 1 is continually communicating and beaming information back to Earth. There were signals that showed that it had finally made it into beyond the heliopause or the edge of the sun's influence into what's called the Oort cloud, or the beginning of the Oort cloud. Okay, which I'm not really good at understanding that either. I would probably just come up with some weird analogy. But my point here is this is the furthest that we've ever been. We hurled back in the 1970s, I want to say 1972, hurled a piece of space material, right, a piece of metal, way out there in that direction and said, good luck, see you later. And it's still going, right? And it's going like the Energizer Bunny. And it has finally made it over those, that's 50 some odd years, has finally made it to the edge of our solar system. That's really far. But also, when we have these ideas of traveling to different distant stars or different distant galaxies, I just want you to take that into perspective. Of the entire time that we have been doing any space exploration, space flight, putting stuff up out beyond our Earth, this is as far as we have made it yet. Now we can, just like the New Horizons mission that just went out to Pluto, things move a little bit faster than they did at this point. So we can push things a little bit faster to make them go further faster, but still, the point still stands. It takes a long time to get very far from the Earth, okay? Now, a little bit more about Voyager and the rest of the solar system. So Voyager's slightly older sibling, the Pioneer crafts that were also expelled, was an older version of those, and Voyager, as you well know, contained the Voyager disk, with humans saying hello in hundreds of languages, or somewhere around 100 languages. A whole bunch of music from every continent or every country, I think, was able to pick some music. The music sign right here is supposed to play Johnny Be Good. That was what the United States put on ours. So that's the Voyager record, and there was a very similar golden plaque that was put onto the Voyager. But I like this plaque better. This is the Pioneer plaque that was on those previous two, the Pioneer craft, and I like this one. I think it's funny. We have two anatomically correct humans. Notice that they're Anglo-Saxon from every feature we can probably tell here, which go figure, right? And the anatomically correct. So we have kind of naked people like, hey, what's up? And then besides the naked people hanging out, what is shown here is each one of these is showing distant stars, or the stars that are closest to us, and then a map to our solar system. And then within our solar system, which is here, Sun, Mercury, Venus, Earth, third rock from the Sun, is we're essentially telling anybody who has come across this, the thing that they just came across, Pioneer, is giving us a roadmap to where we live, and we're out here nakedly like, hey, come listen to our music, man. So I read this once that, there's nothing better than to give an alien race than a cool mixtape to jam to and inviting them over to your house, right? Hey, come on over. Pretty funny. Okay, maybe you don't think that's all that funny and wasn't worth your 2 minutes of time there. I think it's pretty funny. Okay, well, one last thing. The idea here, of course, was to show that we are not to be feared. We're smiling. We are human. We're happy, and this is where we live. Come tell us if you're around too. All right, now back to protoplanets. After those planetesimals were created, the one thing I want to notice here, or say here that I didn't say on the last slide with this picture, this protoplanet, and since all this accumulation has been occurring, that's the source of Earth's heat. The heat that the Earth still has. We just talked about the layered Earth the other day and the Earth being hot in the interior. That heat is still there from this early process of accumulation. We call this Earth's primordial heat, the primary heat, the primordial creation. And that heat is the kinetic heat or frictional heat that's released by doing this, right? Just slam your hands together for a little while. Not only does it hurt after a little while, but you can feel that gets warm, right? And it is that release of heat from the impacting or from friction that is still trapped within the planet, because rocks are poor conductors of heat and electricity. They can heat up, it takes a while, and it also takes a little while to cool down. They are not conductors. Rocks are not like wires. They don't conduct electricity or heat very easily. So this rock has been holding on to that heat for 4.5 billion years. This is our primordial heat of Earth's early accretion. Now, as we talked about the other day, this was now the time of our protoplanet undergoing layering, undergoing differentiation into layers. As this material all homogeneously spread throughout, the heavier materials beginning to sink towards the gravitational center, being replaced then, or replacing, excuse me, the lighter materials which began to float up towards the exterior. So we have an Earth that's being differentiated into layers until BAM! Whoa, we have a nice, happy Earth. Right? So here's our anthropogenic way to say it's happy out here. It's just a nice, peaceful system. It's calming down, no more big things like meteors, maybe a couple small meteors hitting us. We have volcanism, right? We're starting to get maybe some oceans after all of this material is outgassing out from the interior of the planet, all the gases. It's starting to look kind of like an interesting planet. Until then, bam, we get this huge impact where a planetesimal, this random little planetesimal, the little sister Theia that's out there, still aggravating the Earth's orbit, probably. Previously, maybe we could call this Gaia, like the Gaia of the Greek goddesses, and then that's also what Theia is named after. Theia, this little planetesimal, gets close enough finally to Earth that they exert a gravitational force on one another, and it finally happens. They finally hit one another. And this is not unlike what will probably happen with Pluto and Charon, right? The Pluto, the furthest outboard, you can still refer to it maybe as a planet or a dwarf planet, but part of the reason why it's called a dwarf planet is because it has a planetesimal, Charon, within its system. And eventually those two, they're getting closer and closer and closer and closer, and maybe in about 1 billion years, they're going to collide, and they're going to combine and expel material as a larger planet. And then we can have Pluto back in the club. You know what I mean? Let's come back to our planetary system. This was a planetary system then. These two were probably doing this delicate dance for some, couple 100,000 years before this occurred. But when it finally occurred, it rocked Earth to the core, and that's literal, because Earth started to differentiate into a core, but that process was disrupted by the impact of another planetesimal, that probably also began to differentiate as well. It also had some sort of a core, probably. Now, this is what we refer to as the giant impact hypothesis. And the topic, at the very end of today's class, the topic that we are getting to, the most catastrophic thing that has ever happened to Earth since its birth as a protoplanet. Okay? Now, what happened here, this was probably a glancing blow. This is a computer model. Here's a citation for this. This computer model that shows the way that this was probably possible without obliterating both of these things, because Earth is still around, right? That this was probably a direct blow, but that happened at a vector that didn't go through the center of the planet. And as that occurred, the planet Earth probably stole the heavier material, this gray material representing the iron core, and some of the iron core, or most of the iron core of the planetesimal Theia, accumulated to the planet Earth. So planet Earth got a larger core out of the deal, right? More iron was able to accumulate in the interior of the Earth. That is why Earth has a huge iron core. I know you might not be aware of that or know that right now, but if you look at the other planets, Earth has got a huge iron core compared especially to Mars, which has got a little weeny iron core, and also Venus, which also has, from what we can tell, a pretty small iron core, but not Earth. Earth has this gigantic iron core that takes up nearly half of the planet itself. Not the same as the rest of the solar system, okay, or the rest of the rocky planets. So this computer model showed really well, and it was also repeated by several scientists, that when this hypothesis was proposed by William Hartmann, after some of the data collected by the Apollo astronauts, those data began to suggest that the moon was much different than we thought. And we'll go through some of those observations, and that encouraged William Hartmann, to propose this hypothesis, which was then supported by some of this numerical computer data. So here's a little animation that shows some of this, the moon forming event then, as Theia impacted the Earth. bam, the ejected material, see, most of the planet becomes part of the Earth, but the ejected material then is locked in a gravitational orbit around the Earth. Maybe there were several parts of this impact. The material then accumulated, the leftovers of that material accumulated into what we call today our moon, or what some refer to as Luna, which at the very end of the animation here is being shown. Okay, I think that this is one of the, come on here. Uh-oh. There we go. This is a really fascinating hypothesis, and again, we need to say, and I need to say and state again, that this is just a hypothesis. And it remains a hypothesis because we cannot collect a lot more data about this. But those data that we have are supporting of this hypothesis. So here's the original abstract from this by William Hartman and D. Davis back in 1975 is when this abstract was published at a conference. And exploratory calculations using accretionary theory are made to demonstrate plausible sizes of the second largest, third largest, etc. bodies at close planet formation in heliocentric orbits near the planets, assuming asteroid-like size distributions at the start of the calculation. Why did I just read all of that? It's gobbledygook, right? Now, the rest of this is going on. Collision of a large body with Earth could eject an iron-deficient crust. There's part of these observations that were so crucial to coming up with this hypothesis. Iron-deficient crust. So let's move on to some of the material that support this hypothesis. Shortly, 1975, shortly after, just 6 years after humans had landed on the moon and gathered some rocks from the moon and brought those back to the Earth, where they were chemically analyzed to find that the basalt, the lava flows of Earth, the Maria, and then the lunar highlands, the gabbros or anorthosites of the crust, were very iron deficient. We also did some radiometric age dating of those to find out that the lunar uplands are like 4.5 billion years old. They're just shy, well, 4.3, they're just shy of this age of the impacting event. Okay, that's why this is proposed as 4.48 billion years ago. And then the lava flows are 3.8 billion years old, meaning that the moon is not active geologically. There's nothing that has happened geologically besides meteor impacts in the last 3.8 billion years. Now those rocks then, when brought back and were able to be analyzed by geologists and other mapping of the moon, here's some of the key observations. And the moon has a really small iron core relatively to the planet Earth. And this was done by seismometers that were placed by the Apollo astronauts, and those micrometeors, again, going back to seismology, being able to image the interior. We know that moon has a tiny, tiny iron core. Moon also has a lower density overall than the Earth. Of course, it has a smaller iron core, but overall, the whole thing is iron deficient. Samples indicate that the surface was once molten. Those anorthosites of the surface, they're like gabbros. They're crystalline, intrusive rocks that cool relatively slowly, leaving larger crystals. This hypothesis is also consistent with the nebula theory of formations of solar systems. So this other independent theory that's out there, a theory, one that much evidence has been accumulated and supporting, this other independent theory also supports this thing was probably commonplace in not just our planetary system, but every planetary system around every solar system that has planets. This is par for the course, that planetesimals run into each other, create protoplanets, and those protoplanets are continually bombarded by smaller asteroids, but also may be the site of impacts by other planetesimals. Par for the course for creating a solar system, as you will see in that online model. And lastly, the Earth's spin and the moon have similar orientations. So they're actually locked together. This is why we see the same side of the moon all the time, because they are rotating at the same rate. So we see the illuminated side of the moon. It's not that the moon doesn't revolve, right? It has it has a rotation to it, but it's rotating at the same rate that the Earth is also rotating. So there's similarities and commonalities to both of these systems. These are some of the strongest pieces of evidence, and there are more that exist. Some of the details here, this occurred 4.48 billion years ago. I'm not sure that I had said that number specifically, but that is the age we're looking at. So in our overall 10-week long of this course, the Violent Earth course, and placing these events in the days, this happened on day 1, 4.6 billion years ago, the origins of the solar system and the Earth herself, and this happened halfway through the first day, right? Catastrophic initially occurring. This would have been Theia, the protoplanet, probably the reason that it was all messed up on its orbit is it was affected by when its growing mass exceeded the threshold of approximately 10% about Mars's size of Earth. So as it was accumulating mass, it finally got large enough that the two, after passing about 10%, that the two were inevitably going to interact with one another. Theia collided directly with Earth instead of barely swiping it, so it wasn't just a completely glancing blow off to the side where Theia got ejected somewhere else, but instead, the collision speed may have been higher than originally assumed, and this higher velocity may have totally destroyed Theia. It was either accumulated onto the Earth for the most part, or it became the moon and some other probably near-Earth asteroids that come around in the trajectory of our solar system, not infrequently. There are alternative hypotheses, as I've said, in the scientific method. It's very important to keep alternatives in mind. There are alternatives that exist, but the data, those data don't support these hypotheses regularly. But let's keep them back there so any new data that come along, we can compare these to. Gaia Theia impact maybe was later. Okay, that's not really an alternative. That just means that maybe it was later. Okay? Earth had two moons that collided together to form Luna. So maybe these were two smaller satellites that were surrounding the Earth that formed in some other process, and then those two combined to form one larger moon. Okay? Maybe that's what happened 4.48 billion years ago. Or maybe, quite possibly, Luna, the moon, was formed elsewhere in the solar system and was hurtling across space and got close enough to the Earth that it became a captured asteroid. Okay? And now is a satellite. And that's not unheard of. There are many other satellites out there circling other planets, like, say, most of the 63 satellites around Saturn, around Jupiter. Most of those things are not satellites or moons in the same sense as our moon, but they are captured asteroids. They were pieces of debris, space debris, they got close enough to Jupiter that they latched on. So we know that exists elsewhere in the solar system. Why not in this case? Those are great alternatives. They're not quite as well supported by some of the other observations from the moon, but we will, of course, respect those and keep those as alternatives. Now, here's again that image showing the Earth and Luna way in the distance, and this is to scale. Now, slowly, Luna is drifting away from the Earth at about 3.8 centimeters each year. This has been occurring since prehistoric times and will continue. And eventually, if you enjoyed the 2017 Great American Eclipse, or if you're looking forward to the 2024 eclipse that's going from Texas up towards the eastern seaboard, I think maybe through New Hampshire, the total solar eclipse only occurs because the distance away from us to the moon is a perfect ratio, or about 100 times shorter distance from the moon to the sun. And also the sizes of those are perfectly ratio, is a perfect ratio. I just explained that very horribly. Okay, let me back up. A total solar eclipse is only occurring because the angular distance that the moon makes up if you were to look at the moon in the night sky, that angular distance is exactly the angular distance of the sun. And it's not because the sun and the moon are the same size. The moon is tiny and the sun is huge. It's because the balance between their size and the distance away from each other is perfect right now, perfectly succinct, where we can get a total coverage of the moon, the disk of the moon over the sun to block out that light and make a total solar eclipse. In about 2 galactic years, which is 2 solar system going around the galactic center of our galaxy, the Milky Way galaxy, each one takes about 250 million years. In about 2 galactic years, it's a long time, the moon is going to be too far away to make a total solar eclipse. So good news there is none of us are living in 2 galactic years from now, 500 million years from now. So we will have the good fortune to observe total solar eclipse for the rest of your lifetime if you're an eclipse chaser. Okay? Today's dose of violence was brought to you by William Kenneth Hartman, that was the pioneer of this hypothesis, that went out on a limb with a lot of that early data from the Apollo missions, and he went out on a limb and suggested that this was possible by looking at those data. And then later, more scientists, that was again early in this state of a hypothesis, more scientists were able to independently verify this through other methods, particularly computer simulations, as we saw, that support that this is actually possible, and that the observations and the possibilities all come together that this is the strongest hypothesis that we have for the origins of the moon in the night sky. And I think that's quite beautiful, beautiful story, just as good as any mythology that exists out there. This isn't mythology, this is scientific knowledge. Okay, so that's the end of Violent Earth Lecture 3, I suppose, our violent origins. And next week, in the next couple of videos, we'll be moving on to Earth's deep freeze. Okay, the ice ages. And we're not talking about the most recent ice ages where there were mammoths and giant sloths. Yeah, we'll talk about that one. But also a greater deep freeze that happened even further back in Earth's past, known as Snowball Earth. Okay, until next time, we'll talk to you in a bit in Violent Earth.